Hey everybody, this is my video tutorial for grade 12 biology students at the beginning of the year starting to study the biochemistry strand. And one of the first things that you're going to be doing is reviewing some grade 10/grade 11 chemistry concepts. And I've got a topic here which is called atoms, molecules, and chemical bonds. And while your exact grade 12 teacher may not cover it in this fashion and with this worksheet that I've got for you, this is still the way that I typically have done it for many years, and it is a worthwhile way to review chemistry and learn some new concepts that are part of the grade 12 biology course that you will need throughout the course. So I've put together this video tutorial for you, and I am, of course, hopeful that it's going to help you. I'm open to any questions. If you want to contact me through YouTube comments, or if you want to search me and find my Facebook, or email me through my website, zerobio.com, you're welcome to do that. But here we go, atoms, molecules, and chemical bonds. So there are some materials that you will need in order to get the best out of this tutorial, all right? And the first one I'm indicating right here is a printout from my website. And of course, my website is listed down here. It's www.zerobio.com if you're not already familiar with that. And what you're going to do is search on my website for a printout, and I'll put a link in the information section to that exact printout. It's a PDF file called Atoms, Molecules, and Chemical Bonds. So you'll need that, and I'll be using that throughout this video tutorial. At the end of the printout worksheet, there are some questions that I would typically assign my students. And again, your teacher might assign them, they might not. You might want to try them in order to, learn some of the concepts. And they come from the Nelson Biology 12 textbook. Now, that's the textbook that they use at the school that I just finished teaching at. And it might be a textbook that you use elsewhere in Ontario or somewhere else in Canada. If not, you can get a downloadable copy of this, I believe, as a PDF. I found it and I've got it, and I imagine you could find it as well. But again, that's not really used until the end for the questions. I might refer to it a little bit here and there, but it's not critical if you didn't have that book. But if you have the printout and you follow this video, you'll be in decent shape, I would hope. This is a free video tutorials. Many of my resources on Zerobio, the songs that I've done, written for students and for science, and there's a bunch of them, have all been free. I'm a retired teacher now, and I need to supplement my income in order to continue to pay for my website, which I do pay for, and for the software that I use to make these videos and the graphics and the Flash stuff, and not to mention the music stuff that I use for writing songs for science. So while this is a free video tutorial and I am happy to do that, I am also grateful for any donations that you might feel like making, no matter how small. Everything helps. And future videos at some point will be for some kind of charge. It will not be very much, but it will be something to offset the expenses that I have and to pay me for my time and energy for doing this. And I love to do this, and I'm happy to help you. But feel free, if you are of that type and you want to donate and help out the cause, you can go to my website, zerobio.com, and on the homepage and various spots throughout the website, there are places where you can donate through PayPal if you feel comfortable doing that. It should be no problem. And thank you very much for considering that. But without any further ado, let's jump into atoms, molecules, chemical bonds. I'm going to assume that you have the printout. And if you do, then the part of the first page will look something like this. Atoms, molecules, chemical bonds. The course code is SBI 4U. grade 12 biology. And this is somewhat of a review initially, and then it'll get into some different concepts. Now, I already have the answers to all of this, and I am going to click through this, and that will load some text into the spaces here, and your task would be to follow along with me and fill in the blanks. There will be a number of drawings to make as well. So if I go a little bit too quickly, because I've already got them done, and I will be explaining as I reveal the images and terms, feel free to pause this or rewind and go back again. All right? One other thing I should say, because I hear a little bit of barking in the background, I do have 3 dogs. They may make an appearance either physically or in terms auditorily. Is that the word? So just forgive that. All right. One of them is pretty young, and he gets very rambunctious and afraid of every little thing. All right, here we go. So this is going to be somewhat review at first. So just settle in, relax, and feel good about what you're learning and what you're doing and what you already know. All right. Okay, so I'm coming up to the first blank here. I'm going to click on that, and as you can see, I have revealed the term that would go in that first space. So all of these words are going to be written in all caps just to make them a little bit more visible and in red color. Okay, so atoms are the smallest particles into which matter can normally be divided. Now, that should be no surprise to you. Everybody knows that matter is composed of atoms. Of course, we then have molecules as well. Remember that atoms make up molecules. So, for example, if we just come over to the side here, I've got an illustration of something I'll talk about later. This is a water molecule, and I'll talk about why it's shaped like that and what these lines represent. And this is an ammonia molecule, NH3 ammonia and H2O. These are molecules, all right? Oxygen would be an atom, hydrogen is an atom, and nitrogen is an atom. But these atoms are put together and held together by chemical bonds, which we'll be discussing later. And so atoms make up molecules. And as you can see in the title, atoms, molecules, and chemical bonds. But atoms are the smallest particles into which matter can normally be divided. Now, we say that normally be divided because it is not an easy thing necessarily to break an atom apart. There are electrons, and we'll talk about those in a moment, that are on sort of the outer surface of an atom, and they can be removed relatively easily. But to break the atom apart, that's essentially like an atomic bond, especially the nucleus, to get in and break the atom and release, let's say, protons or neutrons, split that. You've heard the term nuclear reaction, right? And that's not something that you see every day at Walmart, nuclear reactions, all right? So that's what you need to some extent to break atoms apart. So matter can normally not be divided further than the level of the atom. Okay, so that's what I'm getting at there. So examples of important or common biologically important atoms, and I bolded that because there are many atoms or elements that you will have seen in the periodic table, but the ones that we really care about in biology, as opposed to, say, a chemistry class or maybe even physics, these are the ones, all right? Carbon, hydrogen, oxygen, and nitrogen. Now, I've only written their symbols. I'm hoping that you're familiar with many of the elements of the periodic table and already have a bunch of them memorized. And if you don't panic about it, but you've got your work cut out for you, all right? So for now, memorize these ones. Carbon, hydrogen, oxygen, and nitrogen are the major atoms in most biologically important molecules. And you will be studying biologically important molecules later, and I'll probably do a video for you about that. So when you talk about glucose, you may have heard the chemical formula, C6H12O6. All right, C6, there's carbon, H12, there's hydrogen, O6, there's oxygen. All right. And that is a biologically important molecule. DNA, amino acids, lipids, all of which you'll be studying this year. If you haven't already seen them a little bit in grade 11, and you possibly have, maybe even a bit in grade 10, you'll be delving into them quite deeply. And that's really where the chemistry or the biochemistry component of this course comes in, studying those molecules. So it's not like you're going to be learning many chemical reactions that might not make any sense or have any relevance to you, all right? You're going to be learning the important molecules that make up living things. So it's fascinating. Yes, it's complex, but try to get used to that. Try to get used to the feeling of being a little bit confused, a little bit lost, but that sense of wonder, and be proud of the complicated material that you're learning. It's very interesting. All right. Atoms, which we have been talking about, are composed, and I've mentioned this already, of three types of subatomic particles. These are particles under the level, under the level of the atom, or smaller than the atom. They make up the atom. Three particles. Negatively charged electrons, positively charged protons, and uncharged neutrons. Neutral neutrons. All right, so we have negative electrons, positive protons, neutral, uncharged neutrons. Those are the subatomic particles. Now, you may have heard about other particles or strange things in physics somewhere or in some of your reading perhaps, but we are sticking to this stuff, all right? The latter two particles, meaning the protons and the neutrons, are found in the central nucleus. And we'll have a look at a diagram of a typical atom in just a moment. All right, so the protons and the neutrons are in the nucleus, whereas the electrons are located at various distances from the nucleus in regions called energy levels or shells. So we're going to look at a diagram, like I said, in a moment, but you've got the nucleus with the protons and the neutrons, and then the electrons are located at various distances, going out from that central nucleus in regions which are called levels or shells, or energy levels or shells. And they travel, those electrons travel in paths called orbitals. I mean, think of a satellite orbiting the moon, right? A satellite is a big thing, or a planet orbiting. Well, electrons are tiny microscopic structures. So the paths that they take, all right, the actual like roads that they follow are called orbitals. So electrons orbit the nucleus, but the paths that they take are called orbitals. Those orbitals, those roads that the electrons take, can be at various distances from the nucleus. And so those are the energy levels or shells. So let me show you a diagram. Now, there are lots of different types of images of the atom that you can have a look at on the internet. This is the one that I've drawn for this worksheet. So I would encourage you to draw the thing as well. Okay, so how are we going to do this? Maybe I'm going to do a little bit of labeling as well. All right, so I will point out a couple of things to you here. This is my model of a typical atom. And this region right here, that represents the nucleus. Inside the nucleus, I've drawn slightly different colored particles. This one here, maybe that's a proton. And this one here, maybe that's a neutron. So in this particular atom, there would be 2 protons and 1 neutron. I'm just making stuff up, all right? In fact, the number of electrons I've got doesn't correspond to the number of protons and neutrons. So this is not a real atom, it's just a model of a typical atom. So we've got a nucleus. Now you're going to note that there is a line here, a very faint line sort of showing the boundary of the nucleus, but it's not like the nucleus of a cell. There's no nuclear membrane. There's no line there in reality. It's just a region where the protons and the neutrons are clustered together. Now, these dotted lines, and I'll label this one here. This represents an orbital, which is the path that the electron will take, or electrons. Each black dot represents E, an electron. So you can see here, this dotted line here, and there are 2 electrons, and I've drawn one at the top and one on the side. And the reason for that is because you'll be drawing Bohr diagrams, Lewis diagrams, or Lewis dot diagrams, and this is a good way to do it, and I'll talk more about that in a bit. I've also drawn another dotted line a little bit further out with 2 electrons, 2, 2, 2. The dotted line represents an orbital. So let's imagine this electron here is traveling in this direction. And, you know, this electron here is traveling in this direction. Let's say they're going clockwise around the nucleus. So that dotted line is therefore the orbital. And the road, in other words, or orbit or orbital that they're following is a spherical or circular orbital. All right, circular road, just going around like a racetrack. You can see up here where I said S, P, and D. Now, we're not really going to get into that stuff in the grade 12 biology course. That's other chemistry where you will learn about the different shapes or patterns of orbitals, whether they're spherical or dumbbell shape or even more complicated. All right, and there's other orbitals. There's F as well. There might even be more for all I know. So there are electrons traveling around in orbitals. Now, it's difficult. I find it difficult to indicate, excuse me, where the energy level or shell is exactly. And the way I like to explain it is I like to say that imagine these electrons can travel around at this spot on that dotted line. But what if they were a little bit closer to the nucleus, or a little bit closer, or a little bit closer? Imagine this is a certain amount of space, distance. You know, like you've got runners going around a track, and some of them are on the outside part, some are a little closer to the middle and closer to the middle. I consider that to be the energy level or shell. Okay, so this will be the energy level, or just level or shell. So you can have electrons going around in a circle, a spherical orbit or orbital, like I've drawn here, very close to the nucleus. You can also have electrons going around in a spherical orbit further away from the nucleus, so at different steps or different levels. Okay, so get that diagram down, and I'm going to go ahead and clear this so it's not a real mess on the page. If you need to come back in the video, you just do that. Okay, so let's carry on. Most atoms have more than one electron, unlike hydrogen. Hydrogen is atomic number 1, and it only has 1 electron. But most atoms have more than 1 electron. The first energy level or shell is closest to the nucleus, and that's what we talked about here, the first energy level or shell. And it can only hold a certain number of electrons. It can hold 2 electrons. And I've drawn 2 electrons here in this first orbital or in this first energy level, all right? Imagine that there's just no more room, okay? Closest to the nucleus, there's just no more room. They'll bump into each other or whatever, all right? So it can hold 2 electrons. But if the atom has more than 2 electrons, you have to have a place to put them. Once 2 electrons occupy that first energy level or shell, then they move up to the second energy level or shell. The second energy level or shell can hold 8. And I've actually drawn 8 in this diagram here to illustrate this shell is now full. So, I mean, you know, I often use the analogy of like a car or a van or something like that. The front seat, which is the first shell, can hold 2 people, okay, the driver and a passenger. And then you go backwards. You know, the second part of the car has a big long seat, let's say, and you can put a bunch of them, all right? And then you keep going back and filling them up further and further. So 2 electrons in the first shell, 8 electrons in the next shell. How many in the next shell? Well, there is a formula that you can use for all of these energy levels or shells, and it's 2n squared. N represents the energy level or shell. And so, let me go back to this. 2n squared. If we wanted to look at the first shell, you would go 2. N is the energy level, so it's 1 in this case, the first shell, squared. And that gives you 2. The second energy level, you go 2, okay? You plug in a 2 for that n squared, and you get 8, and so on. So you can figure out how many electrons would be in, the fifth shell using that formula. Now, the electrons are really the important part of an atom in terms of how that atom will interact with other atoms. The electrons are like the skin of an atom. And for us, when we interact in society and we shake hands or something like that, it's the skin, it's the outer part of our bodies that interact with other people. It's not the flesh and bone and interior organs, which keep us alive, but it's not interacting with the environment. Those electrons, though, are critical in how the atoms interact with each other and how they bond. So we need to look at diagrams which are called Bohr diagrams or Bohr-Rutherford diagrams after the scientists who created them, so that we get a picture of the atom. Now, you will have done this, all right? And so at this point, this should be review. Now, if it's not all fresh in your mind because you did in grade 10, then you don't worry about it. But at this point, you probably are saying, yeah, this is pretty easy. I remember all this. And that's great. That's the whole idea, that you get a good grounding in the basic stuff so that when we go on and do the more complex stuff, you're not lost on this stuff. All right? So now I will tell you that different teachers may draw Bohr-Rutherford diagrams differently. And it just doesn't matter. If you understand the concept and you know what they're showing, it doesn't really matter how you draw them. All right, so what I've got down below is a space for you to draw, and I'm going to do 1, 2, 3, 4. I'm going to do 5 of these, and you're welcome to do a couple more if you're interested in doing them, but I'm going to choose 5. So I'm going to click on this first one, and we're going to draw hydrogen. So it might be helpful for you to write an H down here, leave some space, so that you know that this is the Bohr diagram for hydrogen. Okay, so I'm going to show it to you. I'm going to get you to draw this. What the Bohr diagram shows is a circular region here which represents the nucleus. Inside the nucleus are protons and neutrons, as you know. And outside of the nucleus are electrons. Now, here's the thing. Hydrogen, which is the simplest element, has no neutrons. It only has one proton and no neutrons. Therefore, when we draw the Bohr diagram, we just write 1p plus. That plus sign indicates that this is a positively charged proton. That's all there is in the nucleus, no neutrons. Hydrogen also has just one electron. Now, we're going to talk in just a second about atomic number and how you can figure out the number of protons and neutrons and electrons, etc. But for the time being, just take my word for it, hydrogen has one electron. It is atomic number 1, right up at the top there of the periodic table. Now, I have drawn a dotted line. You don't have to draw dotted lines if you don't want to, but I like to do it this way. And I've drawn my one electron here. Now, these electrons, this electron, it doesn't stay still, right? It's not out of gas. It's going to be whizzing around. So where you draw it, it really doesn't matter. I just tend to draw it in the top position. This is a Bohr diagram or a Bohr-Rutherford diagram showing the general structure of hydrogen. Now, I want to show you atomic number 2, the second element of the periodic table. If hydrogen was here, let's say on the left side, as it often is illustrated, and you went far over to the right side because of the way the periodic table is put together, you would get helium, symbol capital H, small e, helium. This is how we draw helium. Helium has an atomic number of 2. Because of that, it has 2 protons. So I've drawn 2 protons in the nucleus. And it also has 2 neutrons. Now, the way that you'll figure out how many neutrons, because it's not listed typically on the periodic table, is you will have to take the mass number or the atomic mass of the atom, and we'll talk about that in a moment, and subtract the atomic number. So it's mass number minus atomic number. You'll see that in just a second. It turns out the mass number for helium is 4, so 4 minus the atomic number of 2 gives you 2. So there are 2 neutrons. Now, when you write neutron, you go N and a superscript of 0, indicating that it's neutral. and it has 2 electrons. All right, and these are all just neutral atoms at this point. So I like to draw these separated from each other. And I mean, yes, they are an electron pair, if you know about that, but I highly recommend that you draw electrons starting at the north, at the very top, and then the side and the bottom and the other side, going around the compass. The reason for that deals with particularly covalent bonding, and I believe you will find it helpful to do it that way. All right, let's move on. Lithium, atomic number 3, symbol Li. Lithium has in its nucleus 3 protons, so 3p plus. And because of its mass number, you can calculate it has 4 neutrons, 4n0. Because it has 3 protons, and this is a neutral element, lithium also has 3 electrons. The first 2 electrons occupy the first energy level or shell. And as we said earlier, that energy level or shell is now full with those 2 electrons. There's another electron though, so what's it going to do? It's going to go into the next energy level or shell further out, okay? So there is 1 electron in the second shell. And you'll note that I drew it back at the top, and I'm going to continue in this process as we go through it. Now, I do want you to see the relationship between lithium and hydrogen, which is at the top of that first family. Hydrogen is not a metal, the metals being on the left-hand side. Lithium's a metal, and sodium and potassium. Hydrogen isn't, but it behaves somewhat similarly because it's got that 1 outer electron. Lithium also has that 1 outer electron. And this is an important trend in the periodic table, that the elements in the same family, okay, the vertical column, all have the same number of outer electrons, and therefore they react somewhat similarly. That's very important. And this is why we're looking at these diagrams, to see some of the similarities. Now, I'm not doing all of them in order: hydrogen, helium, lithium, beryllium, boron, and all that kind of stuff. You probably did that in grade 10, or maybe you'll do that in your grade 12. I'm just focusing on a few of these to show you how to draw them. Carbon, as we had said earlier, one of the biologically important atoms, probably the most important atom for life on Earth. This is the Bohr diagram. In the nucleus are 6 protons. Carbon has an atomic number of 6, so 6 protons. It has a mass number of 12 typically, all right? We're going to be talking about that in just a minute. And therefore, 12 minus 6 gives you 6 neutrons. So we also have 6 electrons. These are neutral atoms, 6 protons. You got to have 6 electrons. 2 of those electrons are in the first shell, as you can see here. All right. Now, there are 4 more electrons. They are going to go in the second shell. The second shell can accommodate 8, so we have plenty of room. Where do we put these things? Again, I highly recommend you do 1 at the top, 1 at the side, 1 at the bottom, and other side. Don't go pairing them up, all right? That's not how carbon is going to bond. It's going to bond like this, all right? So there's the Bohr diagram for carbon, and I'll do 1 more, which is sodium, which is atomic number 11. So we are therefore going to have 11 protons in the nucleus. The mass number for sodium is 23. We're just rounding these all to the nearest whole number. So when you subtract that, you get 12 neutrons. Now, if you don't know a lot of this stuff from the periodic table, the symbol for sodium, the atomic number, the mass number and stuff, you're not necessarily expected to, but you'll need a periodic table, and you study it, you get used to it, you know how to use it, and you're set. All right, there's no need to memorize tons of stuff, but you probably will over time just learn these things. So we need to deal with 11 electrons. 2 electrons are in the first shell. Now have a look at what I've done in the second shell here. Because we have 11 electrons and we've used 2, we have 9 more. 8 of them will go in that second shell, and that second shell is then full with 8. That's all it can hold. So I started, here, let me show you with my pen here. All right, I'll stick with blue for now. I started with this electron here. 1 there, 1 there, 1 there, 1 there. After that, I started pairing them up. All right, so I put down the first 4, and then I paired them up. And this is the way that I learned to do it years ago and the way I've always done it. And I think it's a reasonable way of doing things. You put them out, first of all, on their own. And if there's no bonding going on, then you start pairing them up. You'll see what I mean in a bit. There's one more electron. That goes in the third shell, right back up at the top. All right. And if we continued with Bohr diagrams, we would just keep adding electrons, etc., etc. We will not be going past the third energy level in this course ever. All right. The biologically important atoms that I've mentioned to you, carbon, hydrogen, oxygen, nitrogen, and then when we get to phosphorus and calcium, stuff like that, they're all using the first 3 energy levels. All right. We're not going past that, so don't worry about that. So hopefully that's just a quick review for you about Bohr diagrams. All right, so we're going to move on. Hopefully you've got all those diagrams and you're still with me. Okay, so let's get into a little bit of theory. The atomic number of an element is determined by how many protons it has. And this is, I've already said. So you look at the periodic table and you see atomic number 1, 2, 3. This is the number of protons. Now, gold has the symbol Au and has a value of 79. So 79 protons, we don't want to draw that, do we? 79 protons are in the nucleus of gold. This is not something that you should memorize by any means, and neither is this. Mercury, which has the symbol Hg, has 80. The reason that we mention this is that the difference between gold and mercury is essentially 1 proton. Now, they may differ in the number of neutrons, and they're going to differ in the number of electrons, right? Because remember, the number of protons will tell you the number of electrons if the atom is neutral. So if you have one gold atom and it's neutral and it's got 79 protons, it's going to have 79 electrons. If you have one mercury atom, 80 protons, 80 electrons. All right, so that's the atomic number. The mass number, or atomic mass, is the number of protons plus the neutrons, because the majority of the mass of an atom, and the mass is not very big, by the way. In fact, they couldn't even use grams or micrograms. They have to create a new unit for atoms you'll learn about in chemistry. So the mass, however little there is made up from the little protons and the neutrons. The electrons are so small, they're so insignificant, like a grain of sand. Of course, electrons and atoms are smaller than a grain of sand. But imagine 1 grain of sand in your pocket. It would not weigh you down when you step on the scale. No one's going to say you've gained weight. You've got 1 grain of sand, or 79 if it was gold. 79 grains of sand, what the heck is that going to do? Nothing. So the electrons essentially don't matter. So the mass of an atom, and therefore the mass number, is the number of protons and the number of neutrons. Each one has a unit of 1. So if you had, 79 protons, you have a mass of 79 units. All right. And if you have 79 neutrons as well, you add them together and you've got 158, something like that. I need a calculator for this. Okay, calcium has a symbol of Ca, and its mass number is 40. And you just look on the periodic table, and we're using the rounded number. So if calcium, and I don't happen to know, was 39.8, you round it to 40. All right, and we're not going to talk about why they're not whole numbers, right? Not exactly, although it's related to the next topic a little bit. Okay, so how do you figure out the number of neutrons? You're going to take the mass number and you're going to subtract the atomic number. So for example, calcium has a mass number of 40. That's the number of protons and the neutrons. And you want to get the number of neutrons, you take the mass number minus the atomic number. So 40, that's the mass number, minus the atomic number, which is 20. And remember, that's the number of protons. So if 40 is P plus N, protons and neutrons, and you subtract P, protons, you're left with neutrons. So it just so happens to be 20. All right, mass number minus atomic number. Now, there are different types of atoms for the same element. For example, there are different types of carbon. There are different types of iodine, chlorine, hydrogen, many of them. Think of it like Coke, Diet Coke, cherry Coke, caffeine-free, sugar-free, everything-free Coke. They're all Coke, okay, like Coca-Cola kind of thing, but they're all sort of varieties of Coke, all right? This is the concept of the isotope. There is carbon-12, there is carbon-13. They're different types. It's still carbon. Let me show you what I'm talking about here. In this space, let's write down this symbol right here. This is the formula, notation, that's the word I'm looking for writing a carbon atom. Now, there are different ways of writing this. This happens to be the way I'm writing it. It's a pretty standard way, but don't be surprised if you find the 6 is under the C or the 6 is above the 12. What this is, and you may want to write this down, C, of course, is the symbol of the element, carbon, and the bigger number up here is the mass number. All right, so the mass number we were talking about up here, this is the mass number. The mass number for carbon is 12. The smaller number, 6, that's the atomic number. Now, the atomic number tells us the number of protons. Here, let me write a little bit here. Okay, this is the atomic number. And this up here is the mass number. And this is just one sort of notation for how you can write a particular brand or isotope type of carbon. This is called carbon-12. Now, this carbon, can you figure out how many neutrons it would have? We haven't already said it, which we have. You go 12, the mass number, minus the atomic number. There are 6 neutrons in this carbon. So we now know everything. We know the mass number, we know the atomic number, which is the number of protons or electrons if it's neutral, and we know the number of neutrons. Now, come over to this next one. Write this one down as well. There's their symbol carbon. There's our atomic number 6, but this time I've written 13. All right? So I'm going to erase this, so it makes it easier to see. The difference between these two varieties or isotopes of carbon is only this number, the mass number. Now, what actually differed between this carbon? We know we've got Coke and Diet Coke. We know there's the difference. There's some chemical difference in there, or caffeine-free. We know there's caffeine in one, there isn't caffeine in the other. What's the difference between these two carbons? The 6 is the same. Well, it would have to be in order for this to be carbon, because the 6 is the atomic number. And that is what defines an element. It's the number of protons. Because atoms can lose electrons, all right? You've probably heard of ions before, Na+, Cl-. It doesn't go from Na, sodium, and then as soon as there's a plus, what is it now? It's changed. It's gold. We've just converted sodium to gold. It's still sodium. All that's changed is the number of electrons, the skin of the atom, like I said before. The protons will not change, all right? In order to change the number of protons of an atom, you got to break the nucleus and add new protons or remove them. That's a nuclear reaction. Again, not the kind of thing we see at Walmart, right? And so generally, the protons don't change. And so this number is the same between them. This is the number of protons for carbon, happens to be 12. Now, this number, though, the mass number, has changed. And remember, the mass number is made up of the number of protons and the number of neutrons. Well, the protons can't change. So what did change? The number of neutrons. This version of carbon, this isotope of carbon, has one more neutron than this one does. All right? Because it has one more neutron and the neutrons are neutral, it doesn't really affect the way the atom reacts in the world, in the body. All it changes is the mass, ever so slightly in this case. So this is a heavier isotope of carbon than this one is. Now, isotopes you can learn about later on in chemistry or later on in biology are very useful in medicine, especially isotopes, in other words, versions of an atom that have a special quality, like the radioactive, like radioactive iodine, which can be used to study the thyroid gland, which is in your neck, one of the endocrine glands, making a very important hormone, thyroid hormone. And if there's a problem with that and we need to study it, radioactive iodine, which is iodine is normally used on the thyroid, and radioactive iodine doesn't make any difference to it. It can be used to study the thyroid. Anyway, I'm not explaining that very well. I'm not going to get into it. But this is the concept of isotopes. And there are lots of different ones. So you should look up a few other ones until you get the idea that isotopes differ in the number of neutrons. And they are called isotopes. Okay? Differ in the number of neutrons, making them heavier, okay, or lighter. And that has various utilities. Again, there's some radioactive ones. Heavy isotopes can be used in nuclear reactors. Heavy water, maybe you've heard of heavy water with a different isotope of hydrogen. Okay, now we're getting into bonding, and I know the video's long. Atoms bond with each other in order to completely fill or empty their outermost energy level or shell. They want to deal with that outermost level, the skin of the atom. They don't really care about the inner core if there are outermost electrons. It's the outer ones that matter. They either want to fill it or they want to empty it, and they want to achieve a certain kind of stability. If we're talking about atoms going from the second shell and out, we are looking at something called the octet rule. Octet meaning 8. Because that outer shell typically, and we, again, in biologically important atoms, we're dealing with the second and third shell. They hold 8 electrons in the outer shell. We're not worried about the 5th and 6th shell and we got 32 electrons or whatever. Forget about that. It's 8. That's what we deal with in biology. All right? That's called the octet rule. They want to get a stable shell. If they have to lose electrons to get down to 8, fine. If they have to gain a couple to get to 8, fine. However it works. Examples of the elements that we care about that want 8 in the outer shell, things like carbon, oxygen, and nitrogen. Admittedly, hydrogen with its 1 electron, right? There's hydrogen, 1 electron. Hydrogen is stable with 2 electrons because that first shell, which is the only shell it will have, is full. That's not the octet rule, but that is a full, stable shell. All right, so the octet really applies to the second shell and the third shell. Okay, in order to fill or empty those shells, okay, with electrons, atoms will involve themselves with chemical bonds. Unless you're talking about the noble gases, helium and neon and stuff, they already have their full shells. They are stable. They don't react because the electrons don't need to go anywhere. Chemical bonds occur when atoms gain, lose, or share electrons. So this is how chemical bonds occur. You can either gain electrons, lose electrons, or share electrons. There is no talk about gaining or losing or sharing protons or neutrons. Those things are important for bonding and for attracting electrons and other atoms, but they are not directly involved with the type of bonding we're talking about. And it's usually the outermost electrons involved in bond formation, as I've said. These outer electrons are called valence electrons. And so that outer shell of electrons, whether it's the second or third or fourth, whatever, is called the valence shell. And these are valence electrons, outermost electrons. These are the electrons we really care about, right? The inner ones are shielded. They're not really involved. It's like the lower layers of your skin, all right? Again, when you shake hands with somebody, it's the outer layers of your skin. That's the important part. So therefore, what we really care about here in biology and in chemical reactions are the valence electrons, the outermost electrons, not the 2 in the first shell, but it's the 3 on the third shell, the outer shell, whatever it is. So these are called Lewis diagrams or Lewis dot diagrams. Now, I'm going to reveal a number of Lewis diagrams down here. I'm going to get you to draw them. I've got 1, 2, 3, 4, 5, 6, 7. They're not that big. They're not as big as Bohr diagrams. All right, so hopefully you'll have enough room to get them in. So I'm going to start with the simplest one, which is hydrogen. For a Lewis dot diagram, all you do is you draw the symbol for the element and you draw the outermost electrons. Now, in the case of hydrogen, there is only 1 electron. I've drawn that electron as a black circle there at the very top, just like I did when I did Bohr diagrams, but there's no circles or shells or anything. This is a Lewis or Lewis dot diagram for hydrogen. Only one electron. Well, there only was anyhow, so this is the valence electron. If we jump to lithium, however, atomic number 3, there are 3 outer electrons in lithium, and check out this. Why are you whistling at me? My light is making some noise there. I hope that's not going to be annoying to you. All right, there's 1 outer electron in lithium. There's 2 inner electrons, 1 outer electron, and so that 1 outer electron is the valence electron, and that's what we draw in a Lewis diagram. And look at the similarity with hydrogen. Now, we mentioned that before, the fact that they're in the same family, it's because of that outer valence electron. This is a Lewis diagram, and it is more helpful to us for bonding than the Bohr diagram. We don't really care about the number of protons and the number of neutrons. We really care about that outer electron. Here's sodium, and I just draw this in comparison. Aren't you glad you're not drawing the Bohr diagram for sodium? 2 electrons in the first, 8 electrons in the second, 1 in the third, and then all the protons and neutrons. The Lewis dot diagram, simple. Na with its dot, with its 1 electron. But that is what we care about, because that's the electron that's going to be involved with bonding, not the other 10 electrons that it has. We got to look at carbon, most important element, okay? Notice I'm drawing them all the way around the compass points, all right? Carbon has a valence of 4. It has 4 outer electrons. 6 electrons in total. 2 in the first shell, 4 in the second shell. It's those 4 that we draw, that we care about. Calcium, atomic number 20. This is usually the last one you would draw as a Bohr diagram. You want to draw calcium? Check it out. Simple. Instead of drawing all those shells and filling up the electrons. Calcium is an alkaline earth metal with an atomic number of 20, so it's got 20 electrons, but only 2 of them are in the outermost shell, and so we draw those 2. And again, I'm going from the top to the side. If there was a third one, I'd put it underneath, and then the 4th one over there, but calcium has a valence of 2. And so do all of those alkaline earth metals. So remember, you got alkaline metals on the left, alkaline earth metals, you got beryllium and magnesium and calcium and barium. They all have 2 outer electrons, valence electrons, and that's what determines how they're going to react. Let's look at oxygen. Oxygen is atomic number 8. So it's got 2 electrons in the first shell. That shell is full. 6 more electrons. We're going to put them all the way around. Now, 1 at the top, the side, the bottom, the other side, then start pairing them up. 2 sides here with only 1 electron. So this is going to show us how oxygen is going to bond, because it needs an electron there and it needs another one there. So it looks like it's going to make 2 bonds, right? And therefore it's going to be stable. Anyways, fluorine, halogen or halogen, fluorine, chlorine, bromine, iodine, all the same valence electrons. 7 in this case, 1 short of the octet. Therefore, very reactive, very aggressive, wanting an electron from somewhere. Somebody is going to give that electron, making this a negative ion. All right, I'm going to move on. You know what? I'm thinking it's my light. I think it's the crickets outside. Cicadas maybe. All right. If an atom loses electrons, it gets a positive charge, right? You lose negative electrons, you become positive. That atom is now called a positive ion. It's also called a cation. I'm not going to get into those names there. Positive ions. They've lost electrons, they're now positive. Examples are things like Na+. Some people write Na+1. They put the 1 there. You don't really need it. It's a superscript. This is the charge. All right. When you lose 1 negative and you still have the same number of protons, the positives, but you've lost 1 negative, you are now positive. All right. And if you lose 2 electrons, you have 2 extra positives. You didn't gain 2 positives. All right. You just lost 2 negatives, so you are now positive. All right. Mg2+ is an example. If, on the other hand, an atom gains electrons, it gets a negative charge and becomes a negative ion, or an anion, if you've heard those words. So if you gain electrons, you become negative. If you gain one electron, like chlorine, you become a chloride ion. There's a minus sign right there. If you gain two electrons, like oxygen, let's say, a neutral oxygen, and I'm gaining two, you would get a 2 minus charge, or a -2 charge, however you want to put that. All right? Now, if you have positive ion and negative ion, those are oppositely charged atoms, ions, whatever, and opposites attract in terms of their electrical attraction, and this is what creates an ionic bond. So here's the first of the three major types of bonds, ionic bonds. Ionic bonds are bonds between oppositely charged ions, and it could be just two, it could be three, it could be a whole bunch of them, all electrically attracted to each other. Now, we are going to draw, I'm going to have you draw the Lewis illustration of ionic bond formation. We're going to draw some Lewis dot diagrams of atoms, and we're going to show how an ionic bond forms. Now, I'm going to show the reaction, and I get you to copy this, and we're going to talk about it. All right? So you may have to pause it once you see the reaction. Darn it. I've got a little mistake in here. So let's see if I can fix that up in there. All right. I am missing, for some reason, fluorine here. I'm going to draw the fluorine atom, and I'm going to go 1, 2, 3, 4, 5, 6, 7. That's what I'm missing. I need to have the other atom. I don't know, it disappeared somehow on me. So we've got a sodium atom with its one electron. I've colored in red so we could follow it. This is one electron, the valence electron. We also have a fluorine atom with its 7 outer electrons. Remember, these are Lewis illustrations or Lewis dot diagrams. Now, when an ionic bond forms, what happens is, I'll go to another color here. This electron is going to be transferred to this atom in order for the second atom, fluorine in this case, to become stable. Fluorine has a strength to it. It's called electronegativity. We'll talk about that in a moment. And if it is in the vicinity of sodium and it has only 7 valence electrons, it wants to become stable, to have an octet. It will pull the electron away from the sodium to itself. And that's why I drew the arrow and I drew the next step. By pulling the electron towards itself, sodium has lost that electron and is now a positive ion, +1 or just plus, doesn't matter if you write the 1 or not. This is a positive sodium ion, and fluorine has gained that electron right there. All right, that's why I did it in red. It is now stable, it's got a stable octet, and it has a -1 charge. Now, I wrote the ones just to make it a little bit easier to visualize the actual amount of the charge, the size of the charge. Now, fluorine is stable because of this. It's become a fluoride ion. Sodium also is, because remember, sodium had 11 electrons in total, 1 outer electron. The next shell down has 8, that's the second shell. All right. So by losing that 1 outer electron, it's like losing weight. I lost 1 pound and I'm down to a smaller, more stable me or something. All right. So that second shell is now full. Well, it was full before by getting rid of that third shell, that 1 electron. These are now oppositely charged ions, and they attract each other electrically. And so you get the final product, which is sodium fluoride, which is an ionic compound made of 1 sodium and 1 fluorine, sodium fluoride. You don't do this. You don't draw Na, oh, what happened here? You don't draw Na-F like I did over here, these lines. That is for covalent bonds, and the dots for hydrogen. I'll talk about that later. So you don't draw that. You just draw them together, NaF. Okay, let me get rid of this. I'm sorry about that fluorine there. Hopefully you've gotten that drawn in. Hopefully I don't have a mistake in the next one. I'm going to clear this, And let's have a look at the next reaction. This is a little bit more complicated, so you're going to pause the video and write this down, or maybe you can write it while I'm explaining a little bit. In this case, we're going to deal with magnesium. Now, I know I'm using atoms that are not like biologically important atoms. That's fine. You have to do it for ionic bonds. So, magnesium is an alkaline earth metal and has two outer electrons, two valence electrons. I've drawn them at the top and at the side. There we go. Let's react this with chlorine. Now, chlorine is a halogen, and it has 7 outer electrons. It needs to gain 1. Well, that would stabilize chlorine, but if magnesium just loses 1 and it has 2, it's got to get rid of 2 in order to go down to the lower shell that's full. Magnesium is not going to be stable by losing 1. It's got to lose the 2. Chlorine goes, look, I got no room for it. I can only take 1. Well, let's get together with another chlorine then. 2 of you guys come together with 1 magnesium, all right? So that you'll get this kind of thing. You go over here. You go over there. Everybody will be happy, all right? Both chlorines will become stable, have an octet. Magnesium loses those outer electrons, goes down to a smaller, stable sense, but because it loses those electrons, it has a +2 or a 2+ charge. This is a magnesium positive ion. Because chlorine gained, it has a -1 charge. 2 chloride ions, 1 magnesium ion of opposite charge, the correct amount of charge to sort of zero out, they are all attracted to each other. This formula is the correct one for this compound, MgCl2, magnesium chloride. It's not MgCl because that can't exist. It's not stable. That magnesium, like I said, needs to lose 2. Chlorine goes, I can only handle 1. So it's not going to work properly. I mean, it might be that magnesium loses 1 and chlorine comes along and then quickly another one comes in, but the end result is MgCl2. These are compounds that have ionic bonds in them. And this is important for grade 12 biology, ionic bonds. All right? Okay, so hopefully you got all that. I'm going to move on to the next part. Like I said before, in order to gain that electron, that fluorine in particular I was talking about, it has to pull it. It's got to have some sort of strength to it. All right? It must pull the electron away from another atom. This pulling force is called electronegativity. It's like Spidey strength, Superman strength. It is the strength of the atom. It is called electronegativity. And the symbol is E with a small n. I don't know if you can see that. The electronegativity is the force of pulling an electron towards itself. The greater that force, the stronger the atom is, all right? The more able it is to gain electrons. So when you go, okay, I've got this atom and I've got that. Here, let's look at this. Fluorine and hydrogen. Which one's going to win, right? When they're going to fight together, which one gets the electron? Well, it turns out that there are tables of numbers, okay? And it might be in your periodic table. The number for fluorine happens to be 4, all right? That's the highest it can be. It's very strong. 4 is the highest, like a grade point average. I think 4 was a typical one, all right? Not typical that students get that high, but I mean, that's the scale they use. All right, whatever. Hydrogen is 2.1. So, which is the stronger element? Fluorine has a higher number, and you can just look these up on a periodic table. Okay, fluorine, chlorine. And generally, the stuff over there on the right side, those halogens, very, very strong compared to the hydrogen and the sodium. Those atoms that tend to give electrons. The metals, they conduct electricity because they give their electrons away. They're so weak. But that's part of life, though. We need that. So fluorine is going to be the one that's going to gain it. Now, these are not numbers that you would typically memorize. It might be nice to know fluorine. You can always look them up at the chart, and then you can figure out which one will gain the electron, which will lose. In the end, we form ionic bonds. That brings us now to covalent bonds. Bonds which are formed by the sharing of electrons. When atoms share electrons. So, you are not getting positive and negative ions. The elements are not actually different enough in electronegativity, different enough in strength, to completely take the electron away. They have similar strengths. So they say, you know what? I'm not stronger than you. I can't pull the electron away. Let's agree to just share the electrons. They are sharing their outermost electrons. This is important because look at the word, covalent. They're not sharing their innermost electrons. They're sharing their outermost electrons, those valence electrons. Now, there's different types of covalent bonds. When identical atoms bond, neither atom is more electronegative, right? They're identical. Two hydrogens, two chlorines, two oxygens. Neither one is stronger than the other. So they end up sharing the electrons equally. And examples are these diatomic molecules, molecules with the same element, two of them, two H's, two O's. All right. Now, we're going to look down here later on at a Lewis illustration of this kind of molecule. There's H2 and this is O2. So we're going to look at some of these examples. The type of bond that gets formed is called a non-polar covalent bond. Now, this is going to be a new concept. All right. Non-polar. There is no pole like North Pole, South Pole, or you know the poles on a magnet? The North Pole and South Pole. There is no difference in charge between the sides of the molecule. One is not stronger than the other. We got the strong one and the weak one. No, they are equal, so there is no difference. This is called non-polar. Now, let me go on and do the next paragraph, and I will explain this better to you with these illustrations. So when identical atoms form, we get something called nonpolar covalent bonds. But when non-identical atoms bond, when they're different from each other, one atom has to be more electronegative, more stronger. They're just different elements or atoms. One has to be different. So they don't share electrons equally. So HCl, for example, hydrogen and chlorine. One of them is stronger than the other, pulls the electron to itself, but not strong enough to completely pull it away, let's say. So they don't form ions. It's like, I'm stronger than you. I get a greater share of this electron than you do. I am more negative now because I get that electron more than you do. So there are poles to the molecule, a negative and a positive. So we're going to draw this in a second. This is a new concept for grade 12 biology. Up to this point, everybody goes, yeah, I learned all this in grade 10, whatever. Now it's new for everybody. And I think from this point on in the course, all right? So here's another example, very typical, water. Okay, you don't have to have two elements, you can have a bunch. You've got three in this case. But because there's oxygens and hydrogens, they have different strengths. They're not strong enough to pull the electron fully away and make ions. They go, all right, fine, we'll share. But it's not a fair share, is it? It's not a fair share. Electrons spend more time around the more electronegative atom, depending on which one it is. They spend more time there because it's stronger. And that gives it a partial negative charge. Now, again, I'm going to explain a little bit more as we go on, all right? Because the electron spends more time around one atom than the other, that atom is more negative because of that electron than the other one. But the other atom, which is somewhat robbed of its electron or electrons, has a partial positive charge. So this is where the poles build up. One atom pulls the electron over to itself and gets it. It's an unequal sharing, but they are sharing. It's like I get you 5 days a week and you get it only 2 days a week. So I'm more negative than you are, okay? So negative and positive are the different charges. They're called partial charges. They're not ions like Na+, a full positive, or Cl-. These are partial charges, and there's a way that we write partial versus a full charge, like Cl-, we don't write it like that. You'll see. The type of bond then that results from this unequal sharing is called a polar covalent bond. So covalent bonds are polar or non-polar, and you're going to have to be able to identify the two different types. Depending, however, on the shape of the molecule, whether it's symmetrical or not, the overall molecule made of these atoms could still be electrically neutral and not have an overall charge, even though it has partially charged ends. Now, like I said, this is a new concept, so this is something we're going to need to delve into. What we're going to draw below here, and I've already started because I'm going to do 1, 2, 3, 4, 5 of them here, and I didn't have a lot of space, all right? We're going to do Lewis illustrations of nonpolar and polar covalent bonds. So what we're going to do, what I'll have you do, you don't have to draw this box here, just draw these symbols. Draw two hydrogens a little bit of a distance away. So you can draw something in between. It's nothing going to be nothing major or whatever. I just wanted it to look big so you can see it on your screen. Now, hydrogen has a valence of one outer electron. It's the electron that we care about, not the protons or neutrons. It's that electron that's going to bond. Imagine one hydrogen here floating around, and it sees another hydrogen. And they say, hey, we should get together and bond. Think of the electron like the eye. It's got one eye, all right? And as it sees the other hydrogen, it's going to look. In other words, the eye is going to move so they can see the other hydrogen. Look at what I'm talking about. I have drawn in the single electron for this hydrogen, and I've drawn it on the right side, not at the top this time. And this one, I certainly didn't draw at the top. I drew it all the way around over here. Imagine that hydrogen has one eye, and they look at each other. These are the electrons that are going to be involved with bonding. All right, so they need to be in close proximity to each other. Okay, here's what happens. The hydrogen on the left says to itself, quote unquote, I'm unstable, I'm unhappy, I need one more electron to achieve stability. It's not going to be the octet, it's not a perfect world, all right, but I need those two electrons to fill in my first energy shell. The other hydrogen goes, yeah, well, same story here, buddy. I need one as well. And you're not stronger than me, so I'm not giving you my electron. This hydrogen says, well, I'm not giving you mine. They go, okay, fine. Look, we're both unhappy. Let's just get together and share. And so you draw the symbol, the electron, that's the Lewis diagram, or the Lewis dot diagram, and then you circle the bond. Now, a chemical bond, in this case, a covalent bond, is drawn as a circle or ellipse or whatever, round or rectangle, around the electrons that are involved with bonding. Now, so why two? Well, this hydrogen on the left has its one electron, and it needs another electron to get two in the first shell, and it'll be stable. But this hydrogen on the right has one electron, and it needs the other guy's electron, so it's stable. So we draw a circle around the electrons, and we call this a bond. This is why they stay together. They go, look, we can share electrons, so let's stay together. We're better together than apart. Because it's the outermost electron, and in hydrogen's case, there's only the one, it's called a covalent bond, a sharing of valence electrons. And there are two electrons always in one bond. This is a single bond. It's one bond. We'll look at double in a bit, and even triple, I think, with two electrons. That is a covalent bond. Now, is it polar or non-polar? That is the question. All right, so here's what I need to use my pen for. All right, hydrogen on the left goes, I am going to pull this electron towards myself like this. I'm going to pull it away. This hydrogen on the other hand says, yeah, well, you know what? I'm pulling the electron over here. And we are equally strong. And so therefore that bond is a non-polar covalent bond. There is no buildup of electrons on the left or on the right. In fact, the molecule as a whole, and I know this is going to seem a bit weird, the bond versus the molecule is non-polar. There's no negative end and positive end. Let me go on and I will make that a little clearer to you as we progress here. So let's go down to oxygen here. Draw an oxygen there and an oxygen here. Now, there's a lot of electrons we have to deal with. And when the oxygens are in close proximity and they are going to bond, electrons are repelled and attracted. They move around. I'm going to show you the way that I would draw those electrons, just like this. Now, there are 6 electrons around each oxygen, and you might ask, well, why is it drawn like that, and how do you know? And I can't give you a good answer. I know the bonding structure, and so therefore I know how to design it, but there's no real rule to say, you know what, start like this and do that. Just for now, draw it this way. Draw 2 electrons on the right side. So like these are like two eyes looking at this oxygen. And the other four, imagine they're kind of pushed away off to the side. They're a little bit shy. So you two go over to that side, you two go over to that side. Do the same thing for this oxygen, the two eyes here, two electrons, two off, two off. Because oxygen has 6 outer electrons, it needs to gain 2, right? Then it'll have 8. So it's not just going to gain 1, then it's going to have 7 outer electrons. That's not going to work. It needs to gain 2. So this is why I've drawn 2 electrons on the side and 2 on the side, because each oxygen is going to borrow 2 electrons. Okay, so let's deal with this oxygen on the left. It looks over here and says, you know what? I got 6 electrons. Can you lend me 2 more? And this guy over on this side goes, well, you know what? I'm the same as you. I'm in the same boat. I got 6 outer electrons. I need 2. Let's just share them, all right? So I'm going to show you the bonds. There's 2 of them. Remember, one covalent bond always has 2 electrons. You do not circle all 4 electrons in one bond. That doesn't happen. So there's a bond here and a bond there. This is called a double bond. This is a double covalent bond. And the benefit is that this oxygen on the right, with its 6 electrons, including those 2, borrows that, that's 7, borrows that, that's 8. And this oxygen, which is exactly the same strength, does the same thing. So it's like it's whizzing back and forth equally. This is also a non-polar molecule. These are non-polar covalent bonds. The electron, this electron, let's say, doesn't spend more time on the left compared to the right. And same for all of these electrons, because the elements are of equal electronegativity. They're identical elements, so equal. Therefore, because the electron doesn't spend more time here or over there, and I'll show you a case where it does in a minute, and you'll contrast that, this is called non-polar. Still sharing valence electrons. These are Lewis diagrams, so it's covalent, but non-polar. Non-polar bond and non-polar molecule. Now, what am I talking about? Let's go on and look at water. Now, you'll notice how I drew water. I drew an oxygen up here, a hydrogen down below, and a hydrogen. It is not O, and H is off to the side. The shape is very important here, and you'll see that a lot in biology. The shape is important. Now, let's put the electrons for the hydrogen. This hydrogen's looking up at this oxygen, so you can place this electron wherever you need. It moves. I'm looking at you. And this hydrogen says, I'm looking at the same thing. I'm looking at that oxygen. This hydrogen goes, look, I really need 1 more electron. I'll be stable. And this guy goes, I need 1 more electron and I'll be stable. They want 2, right? Let's draw the electrons for the oxygen. Now, what are we going to do? Well, we know that 2 electrons make up a bond. So I'm going to draw the oxygen with a dot there and a dot there and the rest just in behind. Okay, so let's do that. There. Looks like some guy's kind of funny hair or something like that. Okay, similar to this, very, very similar. All right, let's circle the bonds now and talk about this. Water is a bent molecule. This is a molecule, right? That's an atom, hydrogen's an atom, oxygen an atom, that's an atom. These are the bonds. This is a molecule made of 2 different types of atoms, 3 atoms in total. And it has this shape. This is the actual shape of a water. It's just the way it is. If you draw this out to the side, you will have problems. All right, so don't do that. This is a covalent bond, and so is this. 2 electrons, single bonds. However, check this out. Now, oxygen is further over on the right-hand side of the periodic table. I know, because I've memorized it, that oxygen is stronger than hydrogen. It has a greater pulling force, a greater electronegativity. You can just look it up in the table if you want to see the number, and it'll find out it's true. And therefore, watch what happens. This oxygen is sitting here with 6 electrons, and it looks out and it goes, hydrogen, you want to bond with me? All right, tell you what. I'll lend you my electrons so you can have the 2. But I am going to charge you interest, and a lot of it. I am stronger than you, and so it pulls that electron over to itself far more often than hydrogen gets it. Like hydrogen, okay, I get the 2 on the weekend. Oxygen gets it 5 days a week. And it also does the same on this side. So there is a net pulling force upwards. All right. And if you were to continue the component or the vectors of this pull, there would be an overall pull. Like if you were pulling a string on an angle that way and another one that way, equally strong, the net result would be a pull forward. Okay? Because of this, the electrons spend more time around the oxygen than the hydrogen, but not always. This is not an ion. This is covalent bonding. Because of this, there is a partial, and we draw it like this, negative. Now, looks like a music note of some kind. It's the Greek delta. This represents a partial negative charge around the oxygen because of pulling the electrons up. Now, it's pulling two, and sometimes people will put two of these or go delta 2 minus. It doesn't really matter. Just minus, but not completely, not like this. Not like you go, oh, 2 minus. That's an ion. This is not an ion. It's not strong enough to be an ion. Hydrogen's still got some strength. It's got like 2.1 strength units, whatever. All right? So the charge that builds up here is part of the time. And because this is partially negative, because it's stronger, hydrogen is partially positive. And I usually do it on every atom, at least a delta plus there and a delta plus and a delta minus there. Interruption with the dogs. But anyways, so that's the situation we find ourselves in. The oxygen is partially negative because it's pulling the electrons towards itself. The hydrogen is partially positive. Not fully, because it doesn't give up its ownership of that electron. It just sort of lends it away. They are sharing, but it's an unequal sharing. Now, the important thing about this is we end up with poles. Look, this end is negative, and this end of the molecule is positive. There are different poles. Therefore, even within this bond, the electron is kind of pulled over to there more often, this electron. So the bond itself, because it's between two opposite atoms, is a polar covalent bond. I'll do another one of those for you in a moment. And the molecule is also polar. It is a polar molecule. Water is a polar molecule. It has a partially negative end and a partially positive end because of this unequal sharing. Let's go on and see another example. Let's draw a carbon in the center with 4 hydrogens symmetrically, and that's important, symmetrically placed around that carbon. This is going to be a methane molecule. Now, let's draw the 4 valence electrons on carbon. And this is why I told you that I think it's very important for you to draw them at the right places, all around the compass points, instead of paired up, okay? Carbon has 4 valence electrons, and hydrogen has 1. Draw the electron of the hydrogen pointing towards the carbon. You can now see, I think, the bond formation that is going to occur. We are going to have a bond right here, and right here, and right here, and right here. So I'm going to reveal that right now. So go ahead and circle those bonds there. The central carbon atom has 4 valence electrons, and carbon needs 4 more to be stable, to get that octet. 4 hydrogens come along, each of them wanting a piece of that carbon, all right? Each of them wanting to get 2 electrons. This is the arrangement that you will end up getting. 4 single bonds, each with 2 electrons. Hydrogen is satisfied, it gets its 2. Carbon is satisfied because it gets another one there, and there, total of 8. But carbon, a little bit further over on the right than hydrogen, has a higher electronegativity than hydrogen. It's stronger. Not strong enough to pull the electron straight away so that hydrogen becomes a positive ion and carbon becomes a negative ion. Nope. This is covalent bonding, sharing. But here's the thing, all right? Here's carbon, stronger than hydrogen. It pulls the electron downwards like that. But down here, it pulls the electron like that. These 2 poles cancel each other out, essentially. Pulls the electron this way, pulls the electron that way. Okay? All of these pulling forces essentially cancel out the net effect. All right? So you'll see what I mean in a second here. What we end up getting is let's go back to this. Partially positive hydrogen here. Partially positive, partially positive, partially positive. And carbon is partially negative, or -4. Some people want to add up how many positives and how many negatives. These are not full charges. These are not ions. They're partial charges. Each of these bonds is a polar covalent bond. Let me switch to just another color for the moment. I don't know if I can find a good one. I'll even black, just to highlight something. If we just took this part of the molecule between carbon and hydrogen, carbon is more electronegative than hydrogen, there would be a pull to the carbon, all right? But this one, so it's like negative is being pulled this way to the left, let's say. But then if we look at this area, also a polar covalent bond, now negative is being pulled from the left to the right. So canceling out from the right to the left, from the left to the right. They cancel each other out, all right? And then if we look at this region, this is a polar covalent bond as well. Carbon pulls the electron down towards itself. It's more negative in the bond in this area than this. This is a polar covalent bond. This is a polar covalent bond. I'm going to erase all of that. But because of the symmetry of the molecule, those pulling forces cancel out. So although the bond is polar covalent, the molecule as a whole is not. And what this really means is that a molecule of CH4 methane is not soluble in a polar solvent like water. Methane is a hydrocarbon, CH4 just made of carbon and hydrogen. It is not very soluble in water or in a polar solvent. And that will become more relevant to you later on. Okay, so I wanted to show you an example of a non-polar covalent molecule with polar bonds. And here's another example. Let's just go on and quickly do the carbon dioxide. I've got a carbon here. I've got two oxygens, all right? And we're going to draw the electrons around the oxygen. Once again, I've drawn the inner electrons here, the ones on the right side, 2 electrons from oxygen facing the atom that it's going to bond with. Same thing with this oxygen, so there's 6 in total, 2 facing in, and then the other 4 just sort of sprawled out, like we did in the O2 molecule down here. Carbon, of course, has 4 electrons. Now, I've drawn them in a different orientation than here. And again, you just have to get used to the shape of the molecule once you learn them. And you're not expected to know them right now, okay? You would figure out where the electrons are. But because carbon's 4 electrons are going to be involved with bonding, then they would have to be positioned like this. You couldn't have them up top and bond with these 2. Anyhow, just go ahead and draw this. Now, carbon has 4 electrons, as we know. It needs to gain 4. So it goes, hey, your oxygen over there. I could borrow this one, and I could borrow this one, and this one, and this one, and we would get these bonds. Carbon, by borrowing that electron, that one, and that one, gets its 8. It reaches its octet, it's stable. Oxygen also says, hey, well, I have 6 electrons. I need to borrow 2, so I'll borrow this one and make a bond. I'll borrow this one and make a bond, and this oxygen does the same. Notice the shape of this molecule is critical. It is linear. They're in a line. It is not like the water molecule, which we drew down here, which was bent. Had I drawn the hydrogens up like this, and the oxygen in the middle and the 2 hydrogens, oxygen would pull from one hydrogen, pull from the other, and the poles would cancel out. You would get a non-polar molecule. But we already said that water is a polar molecule because of its shape, because of the pulling up this way, pulling up that way. The same goes for carbon dioxide with respect to the pulling. Oxygen, by the way, is more electronegative than carbon, so it will pull the electrons in this direction. But on the other side, this oxygen pulls the electrons in that direction. An equal pull. Now, between the oxygen and the carbon, oxygen being more electronegative, it gains this electron and its own more often than carbon does. So there's a partial negative charge right here on this oxygen compared to the carbon, which is partially positive as a result. It still gets the electrons, just not as much. This oxygen, on the other hand, also does the same thing. It's more electronegative than carbon, and it pulls the electrons like that, leaving oxygen, or carbon, sorry, partially positive. The bonds themselves are each polar covalent because of the unequal pulling. But when you look at the entire molecule, the molecule pulls to the left, pulls to the right, and because it's linear, it zeroes out. Now, if this was a different element, if this was fluorine, not identical to the other side, you would then have to figure out which side is more electronegative, but it's not, okay? 2 oxygens, 1 carbon, equal poles. This, therefore, has polar covalent bonds, but is a non-polar molecule. Now, does carbon dioxide dissolve in water very much? No, neither does oxygen. This is why you can't breathe underwater. All right, because there's not enough dissolved oxygen in the water. Look down here. Oxygen, O2, is non-polar. Water, H2O, is polar. They don't mix. They don't dissolve in each other. So if you go into the river there and try to take a deep breath, there is not enough dissolved oxygen to support your life because oxygen doesn't dissolve in water. It's not soluble. It's not polar. If it was polar, it could dissolve. And again, we'll get more into that in later biology and talk about the bloodstream and gases in the blood and carrying of oxygen and hemoglobin and stuff. Same thing with CO2. Carbon dioxide is a non-polar molecule overall, albeit with polar covalent bonds, but the polarities canceled out in the overall molecule. It doesn't dissolve well in water. Therefore, there is low oxygen, low CO2 in water. All right. So that's the concept of polar and non-polar molecules, and it is a new thing for grade 12 bio, and hopefully you are getting that. I want to say a little bit about this diagram I've got here, and then I've got one more thing to show you. This is showing hydrogen bonding, which we haven't talked about, which hopefully you'll be reading about. That's these dotted lines right there and right there. And hydrogen bonds occur between partially negative and partially positive atoms. Oxygen, as we know in a water molecule, is partially negative. Whereas the hydrogens are partially positive. So it's going to write partially positives there. This is an ammonia molecule, N and 3 H's. Maybe I'll look at this one down here. Okay. Nitrogen is highly electronegative compared to the hydrogen. So nitrogen is partially negative. Hydrogen is partially positive, and therefore there is an electrical attraction. But these are between separate molecules. These are within a particular molecule. These are intramolecular bonds, all of these. These are between intermolecular bonds. Hydrogen bonds form between an electropositive or partially positive hydrogen and an electronegative atom like oxygen or nitrogen, all right? So that's just something that you can read about, but it also brings in the polarity aspect. Okay, on to the last page. I want to mention to you that using the Nelson Biology 12 book, there are questions that you can do. If you want to talk to me about them at some point, you can, by all means. There are other types of bonds as well. Here's the hydrogen bonds. There's a diagram similar to the one I've got here in the book on hydrogen bonding. You're welcome to draw that. You possibly may be assigned this anyhow by your teacher. Have one final look at these molecules and try to decide whether or not they are polar or non-polar covalent in terms of their bonding and in terms of the molecule overall. Let's just have a look at it here. Notice that these ones have lines. These are stick bonds. They're not Lewis diagrams. This is the way you'll eventually be drawing most of your molecules. Each stick represents a single bond. That's 2 electrons in the bond. So this represents a double bond right here. This is called a triple bond. Oxygen is more electronegative than hydrogen. So in this case, electrons are going to be pulled this way. It's also going to pull electrons this way, but it's not an equal pull. This is not a symmetrical molecule, and so you are going to have polar covalent bonds in this molecule, and this will be a polar molecule. This is methanol. Oxygen is more electronegative, so the electrons are going to be pulled this way from the carbon and a little bit this way. But in the end, you will also have a negativity building up in this area. Carbon, of course, is pulling the hydrogens this way, and it's not a balanced pull like methane was, so you'll get a polar molecule overall. Two identical atoms, each pulling in opposite directions. These are non-polar covalent bonds between identical elements, and overall the molecule has no pull. All right. This one is interesting because you will have an overall net pull in this direction by this oxygen from the carbon and the hydrogens, and also in this direction. So this is a polar covalent bond. All of these are polar covalent bonds, that one and that one and that one and that one and that one. All the bonds are polar covalent. The molecule, however, has a net pull in this direction and this direction. Sorry, the net pull is zero. The overall pull cancels itself out. This is a type of ether molecule that you'll be studying later, and it is non-polar. So that was a lot of content to study right there in an hour and a half video or so. I hope that helped you out, though. Let me know if you have any questions, and we'll see you in the next one.